Welcome to podcast 8-4, Arcs and Chords. In this lesson we're going to learn three theorems. Theorem number 1 is if two chords are congruent in a circle, what might be true? Well, it turns out there are two things that are true, so that'll be theorem number 2. And the third idea is if a diameter is perpendicular to a chord, what may be true there? When I say what may be true, I'm asking you to measure and guess. So I've given you some pictures already through this sketchpad file, and we're going to look at chords and how they relate to the circle. Theorem number 1. Here is the picture. Grab something and just wiggle it. Drag it around, and you can see that the two chords are given as congruent. What else might be true? Well, let's measure. That is, I've emphasized some arcs. That is, one click was the whole circle. The second click will be just that arc. And if you choose that arc, you can measure that arc, either how long it is or the angle and how it relates to the circle. So I'm going to choose that, and I'm going to measure the other arc as well. Again, you may have to click twice to get just to the arc angle. Now as I move the picture around, dragging a point or the whole thing, the arcs seem to be congruent. Oh, not this way, because what I did is I dragged and created a major arc, and the blue segment or the blue chord's just creating a minor arc. That's just a little bit of a flaw in which I made that. So let's try to keep things both in the minor arc situation. There we are. Everything congruent. Better question would be why? Why is it if the chords are congruent, then the arcs that go with them or the arcs behind them are congruent? One way to do this is to prove through congruent triangles. Congruent triangles prove a lot of different things. So what I'm going to do is just create very roughly here a triangle that utilizes the center with this chord here, and a triangle that utilizes the center with this chord over here. There we are. Given the chords are congruent, what else do we know? Well, what I drew were radii. So all the radii of a circle certainly are congruent. Now what do we know? What we have in these two triangles is this triangle and this triangle must be congruent by the postulate side, side, side. If triangle is congruent, then any parts are congruent. And the part I'm concerned with here is this angle, congruent to that one through C, P, C, T, C. And we're going to find later on in a different lesson, actually the next one, that if the angles are congruent from the center, then the arcs that go with those angles, the arc back here and the arc that goes with it here, are also congruent because they dictate the size of the arc. So if the chords are congruent, the triangles are congruent, which makes these angles congruent, known as central angles, which makes the arcs congruent. Therefore, our theorem is congruent chords create congruent arcs. I said there are two theorems that deal with congruent chords. Here's another situation, but I've also drawn another segment. How does this segment relate to the chord? Notice how they look, first of all, on the way it moves. And it seems to maintain some specific relationship. And if we look at it this way, that is, I'm just going to draw a random segment to this chord from the center. And how is this different than any other random segment? And the idea is that this segment has length. This is the length of the segment. Notice how it moves and the size as I get. Rather large, as big as it'll go, getting smaller, and then getting larger again. So this point right here happened to be the smallest point, also meaning that this segment is the shortest segment from the center to the chord. So I've given you the shortest segment from the center to the chord, and the shortest distance from a point to a segment is the perpendicular distance. So I'm actually trying to discuss the perpendicular situation. So if I have a chord, how does that relate to the distance? That is, if the chords are congruent, how are the distances related? Well, if I measure both of them, so if the chords are congruent, notice the distances are always congruent. And that will be our theorem. Congruent chords are the same distance to the center. The longer the chords get, the closer they must be to the center. The shorter the chords become, the farther away. How would you prove such a thing? I asked myself, and maybe you asked yourself as well. Here's one way to prove it. that if we create triangles, once again, oh, that's terrible, but it'll do. So, given that this is the shortest distance, or perpendicular, and we know that the chords are congruent, then this is the midpoint when we draw from a perpendicular, right down the middle like that. So what I know is, of course, these radii are congruent, and that these are congruent as well, and I have an HL situation. So if the triangles are congruent through HL, that means these distances here must be congruent through CPCTC. Again, the theorem is, if the chords are congruent, then their distances to the center are congruent, or congruent chords are equidistant to the center. Our third theorem, if I have a diameter that is perpendicular to a chord, what might be true? Well, if you're perpendicular to that chord, that means that I'm created a right angle, and like I was saying before, if we create triangles with that, we create a situation in which we have two triangles with a right angle here. So, if the triangles are both right triangles, and these are radii, which means they must be congruent, and this shared side, of course, has to be congruent, then the two triangles must be congruent, in which any parts are congruent. Specifically, from A to this point here, this distance must be the same as from this point to B, this distance. Let's see if that's true in Sketchpad. So I'm going to measure from A to this point here, measure distance, and then I'm going to measure from this point here. That is one click on the point and one click on that. I can measure that distance. No matter how long the chord might be, that perpendicular direction seemed to have cut the chord into two congruent parts. Better word, bisected the chord. What also is true is that the chord is bisected. Notice that, as we said earlier, if this angle here is congruent to this angle here, then the arc created from this angle, that is inside the angle, would be this arc. That arc would be the same as, from this angle, this arc. So it seems like this arc, the entire arc from A to B, must be cut in half. Let's see if we can verify that in Sketchpad. To measure an arc, we're going to choose counterclockwise direction. Click B, click the circle, click E. We can construct and create the arc, and then we can measure its angle. Now I'm going to do that from E, one click E, one click circle, one click A. I can construct the arc, and again measure its angle. And again I see congruence. No matter how this picture may change, we have congruent segments and congruent angles, or arc angles we should say. So the theorem is as follows. If the diameter is perpendicular to the chord, then the chord is bisected and the arc behind it is bisected. Again, if a diameter is perpendicular to a chord, then the chord and arc are both bisected. This has been podcast 8-4, Arcs and Chords. Thank you very much.